framework of the project entitled XGDONT, Decentralized AI and Architectures for Massive Wireless Networking, Slicing, Scalability, and Sustainability. Let me present the results of the Elastic Use Case 1 PoC1 entitled Dynamic Brand xApp. So mainly, the goal of the PoC is to show that it's possible to dynamically modify relevant operative aspects of the RAN to fit the current traffic load and number of users, thus optimizing the utilization of resources and in turn reducing the resulting energy consumption. So mainly in the figure we can see the proposed proof of concept evaluation scenario. The proof of concept builds upon our RAN infrastructure, leveraging its AI-friendly nature, which facilitates the monitoring and dynamic adaptation of the RAN. Towards this end, our RAN has defined the E2 interface, which enables connecting the GNOD in the PoC scenario with the near real-time RAN intelligent controller, which is able to query and control it. In more detail, our RAN has defined the E2 key performance measurement service model, which allows to obtain live measurements from the RAN and provide them to the near real-time rig. Likewise, in E2 RAN control service model has also been defined to modify different RAN aspects at runtime. In the near real-time rig, a predictive AI algorithm will be able to forecast the load of the network by working with the measurements. This enables taking AI-based decisions and implementing the required actions to optimize both the resource usage and energy consumption of the RAN. As observed, the PoC deploys a RAN with two different cells, a coverage cell and a capacity one. During peak hours, the capacity cell enables those users regarding it to fulfill its highest data rate communication needs, whereas the coverage cell constitutes a wider reach, mid to low data rate link for the rest of users. In off-peak periods, it is expected that both the number of RAN-connected users as well as its data consumption requirements will be dramatically reduced. In this situation, the capacity cell might be switched off while the connected users hand over to the coverage one, providing a significant reduction of both RAN resource usage and energy consumption. Likewise, as more users connect back to the RAN and the communication requirements scale up, the capacity cell will be switched on again, providing the required additional RAN resources. In the evaluation scenario proposed by Elastic Use Case 1 PoC1, the near real-time rig acts as a monitoring system, receives the RAN measures, whereas the AI-based prediction algorithm acts as analytic engine, so analyzes the RAN measurements. Also, as decision engine, takes the decisions based on the evolution of the measures, and actuator triggers the capacity cell switching on and off. As it can be observed, the implementation foundations of the PoC are provided by the SRS RAN project, an open source or RAN native 5G CUDU SDR-based implementations from SRS. Among its main features, the PoC relies on its disaggregated design nature to deploy a single CU and 2 DUs that implement L1, L2, and L3 of the coverage and capacitor cells. Additionally, the GNOD also provides the KPM features, and the RC actions. To complete the cells, two commercially available radio units from Manitola, providing the low physical layer, digital and radio frequency front-end functions of each cell. In more detail, the PoC adopts the ORAN split 7.2b configuration, where the DUs hosted in a computing server are connected to the remote RUSB, the front hall interface, employing a fiber link. The other key component of this PoC is the IM framework developed by CTTC, with a RAN traffic load forecasting algorithm as its core. The forecasting of RAN traffic is based on runtime measurements received from the DUs through the rig via the E2 interface. Hence, this AI-based algorithm is executed on xApp in the rig. The ORAN software community near real-time rig is used in the PoC. Finally, the 5G core network is implemented by the Open5Gs open source solutions. All components are interconnected between them using the corresponding or run-defined interfaces, independently of their disaggregated deployment. As for the UE and EU communication, it will happen over the air, although a cable setup is also possible and may be utilized to avoid undesired interferences from all the nearby laboratory setups operating in the same frequency bands. As detailed above, the goal of the PoC is to demonstrate how AI-based runtime time adoption can help optimizing the energy footprint of 6G networks. Towards that end, a simple two-cell scenario is implemented allowing to disable one of them when the number of connected users and their compound communications requirements allows it. To enhance decision accuracy and anticipate future network conditions, the PoC incorporates state-of-the-art AI-driven multivariate probabilistic forecasting methods. Specifically, techniques such as temporal fusion transformer and deep vector autoregressive models are evaluated. These models provide several advantages over classical AI-based forecasting techniques, which typically generate single-point predictions. Such point forecasts often give a misleading sense of confidence and lack the uncertainty quantification needed for safe, autonomous decision-making in real-time environments. In contrast, probabilistic forecasting models offers a fault prediction distribution rather than a single value estimate, uncertainty quantification, including confidence intervals around predicted load, robustness to outliers and anomalies, improving stability in volatile traffic conditions, better support for strategic and risk-aware decision-making in distributed elements. By leveraging these probabilistic outputs, the system can predict future PRB load and determine whether the capacity RU will likely remain underutilized. If low load is forecasted and the coverage RU is predicted to have sufficient resources to serve all connected UEs, the control luxury practically schedules a handover from the capacity RU to the coverage RU and powering off the capacity RU to reduce energy consumption. This proactive energy-saving mechanism is substantially more reliable because decisions are informed not only by observed KPIs, but also by predicted traffic patterns with quantified uncertainty. So, this proof of concept investigates the impact of intelligent run control on performance and energy efficiency using an run compliant architecture. The deployment consists of 2 radio units, each connected to an independent distributed unit, with both DUs aggregated at a central unit. So as seen in the video, we can see that once this deployment has been done, a near real-time rig, 2 DUs controlled by a CU, and a CUT UE connected to the capacity cell, a dedicated KPM collection xApp will continuously retrieve near real-time key performance measurement KPMs from the E2 nodes. These KPMs include metrics such as throughput, PRB utilization, and also RU power consumption, thanks to the use of intelligent chapel appliances that can be integrated in xApp. Thanks to the AP models, we are able to measure those values. So in here we are seeing that CUT-UE is connected directly to the first cell, and we have the rig to control those measurements. Once we have this set up, what we have is that the second control xApp processes the collected KPIs, as we can see in the upper right window, and implements decision-making logic for dynamic energy optimization. This xApp evaluates run conditions, specifically PRB utilization and traffic distribution, to determine whether a handover should be triggered from the capacity RU to the coverage RU. When traffic load decreases sufficiently, the xApp migrates active UEs to the coverage IO, which we will see in a while. And following the completion of the handover, the system powers down the capacity IO, enabling an approximate 50% reduction in IO-related energy consumption as one of the two IOs becomes inactive. Once a handover is completed and the traffic is fully offloaded, as we are seeing right now, the system proceeds to shut down the capacity IO. This action eliminates its power draw, enabling a quantifiable energy reduction. In this POC, disabling one of the two IOs results in an approximate 50% energy savings, directly corresponding to the removal of one IO's consumption from the total network energy footprint. Overall, this PoC demonstrates how our RAN open interfaces and xApp-driven RAN intelligence control on brick enable closed-loop automation by combining fine-grained KPI monitoring with intelligent control policies. The system dynamically optimizes radio resources usage and significantly reduces energy consumption without compromising service continuity. Thanks for your attention.